We continue our set of examples by the Paley-Wiener space. I read.
Javed, it looks to me like the wrong file was shared.
Let me see. Maybe I
think you shared the handwritten one. I sent a typed one.
Okay, there is another one.
Yes.
Okay, there is another one. In the break, I will look for it and share it again. That's the first one. There is a second one too. Thank you.
Yeah, I can post it if you want, if I can find it.
Yes, please go
Okay,
ahead.
I'll go ahead and try and do that.
Please, thank you. Now I want to see my file. What's happened to? Okay. Do you see the OneNote where I wrote the Paley-Wiener space?
Yes.
Okay. That's a very nice space because we use several tools in this one. We need some knowledge of complex analysis and also some knowledge of Fourier analysis. And then it was a wonderful observation by Paley and Wiener. There is a theorem by them, which I will mention. And there is this theorem is like a bridge between the two subjects, and I mean open the road. They both have one book, which with precisely the same title. I mean, it's about Fourier analysis in complex domain, and it's the theorem I will mention. It's just one of the many theorems they found, and you will see even with this theorem we can get a lot. So to prepare for that theorem, let's review some concepts from complex analysis and then from Fourier analysis, complex analysis. We consider functions which are defined on a complex plane to C and holomorphic, so these functions are called entire. But we put a restriction on the growth of this function. I mean, an entire function can go to infinity arbitrarily fast. The restriction we put is this one. Restriction. We assume that there are constants C and A such that absolute value of f of z is less than or equal to C e to the A absolute value of z for each z in C, or at least for large values of z. The constant C is not that important. A is important. And that is why I said if this is true for arbitrarily large values of z, then we can make another C which is bigger. And for this bigger C, the inequality works everywhere. So our main concern is this A here. If a function satisfies this property, we call it a function of exponential type. And the entire function of exponential type. And indeed, in your work before, for sure, you have seen many such functions. For example, f of z is equal to sine z or cosine z. In this way, it is not clear why it is of exponential type, but if you write it as e to the iz minus e to the minus iz divided by 2I, you immediately see that f of z is less than or equal to e to the absolute value of z. So both C and A, you can take it equal to 1. And well, if you study the function On the real line, you see that this is not a good estimation, because on the real line, f of z is bounded, and our estimation is like e to the mod x. It goes very fast. But on the other hand, if you go on the imaginary axis, you see that f of iy is equal to sine of iy, or I sine hyperbolic y, or if you directly use this formula, is e to the y minus e to the minus y divided by 2. And you see that now either in the positive direction or in the negative direction, it behaves precisely like e to the mod z. So the constant a here is optimal, and we cannot do better than that. So this is an example of an entire function of exponential type. And this example also suggests that to look for the best value of a here. And this is called the type of a. So definition of type. We use sigma or sigma of f for this, is the infimum over all a's, where a is the constant which we use here. I can call it star a in star. That's not a good way to write it, but you understand what I mean. In a sense, it's the best exponent that we can put over there, but you need to be very careful with the, if you pay attention to the meaning of infimum. This doesn't mean that there is a constant c such that mod f of z is less than or equal to c e to the sigma z. No, in general, no. Of course, if a function satisfies this, it is entire function of exponential type at most sigma. But if it is of type sigma, it doesn't mean that it satisfies this property. What we can say is that given any epsilon positive, now there is a c, and if you wish, c epsilon depends on epsilon, such that f of z less than or equal to c e to the sigma plus epsilon mod z. This distinction is sometimes important and should be, keep in your mind. For our application, indeed for our the precise form of the Paley-Wiener that we want to study, we can call it semi-type or two growth rate is also important for us. I call them sigma plus and sigma minus. And they are the rate of the growth of sigma on the positive imaginary axis and the negative imaginary axis. Indeed, before giving the definition of sigma plus and sigma minus, it's a good point to give you an exercise. And then you will see why I define sigma plus and sigma minus like that. So exercise, how to find sigma. Show that sigma is given by this formula. It's lim sup z goes to infinity, and that's the point. Z goes to infinity with no restriction on the direction, and any direction it can go to infinity of what? Of a log of mod fz over mod z. This is the formula for the best exponent that we can use, and it gives us the type. Now, I use this to give the definition of sigma plus and sigma minus. And it's almost the same definition. Instead of letting z go to infinity to any direction or any arbitrary manner that we like, I restrict it on z equal to iy and z equal to minus iy. So the first one is slim soup. Y goes to plus infinity log of f of y iy over y. And the other one is lim soup. Y goes to infinity log of f of minus iy over y. So can say in this direction, and the other one is in this direction. The growth of f in both directions. You will see a little bit later why sigma plus and sigma minus come into picture. Well, there's a whole theory, very rich in the theory of entire function, in particular, entire function of exponential type. I don't go into detail. We do not need more than that for the Paley-Wiener theorem. But if you are interested, there are many interesting books, like the book by Boas, the book by Levin, and many others. It's a very classical subject. The other one, which is probably less familiar for some of the students, is the Fourier analysis on R. This is usually a graduate course that we give in master or PhD level. It's called harmonic analysis, and we study this topic. And in particular, I need the Plancherel theory, which is a part of it. Again, very briefly, I want to give you a course which is covered over one semester. So please be patient with what I write here. We start with the function f, which is integrable on R in L1 of R. I mean, more explicitly, integral of mod f dx is finite. And then we have the definition of the Fourier transform, definition of Fourier transform. Is f hat of x defined by integral from minus infinity to infinity f of t e to the minus I 2 pi xt dt. Some comments here. The definition I use here, it's used in Paulsen book, and also in the book by Elias Stein about Fourier analysis. That's not the only way that we can define f hat. In some other textbooks, they define it. So you have to, I mean, bear with pi somewhere. It appears. Some authors define it f of x equal to integral from minus infinity to infinity f of t e to the minus I xt dt. You do not see pi here, but when they show or they present the inverse formula, it is there. Some others, to have a better formula for the Parseval identity, they put 1 over 2 pi, root square of 2 pi in front. Ft e to the minus xt dt. And to make the life more complicated, even there are books in which f hat of x is defined 1/2 pi of the same things. So when you study any book on harmonic analysis, wavelet theory, or the application, one of the first things that you have to verify is what is the definition of the Fourier transform. And the definition has some consequences. And if you compare two books, for example, you may see, we will write it today, even in a few minutes indeed, you will see that in some books they write F inner product with G is equal to inner product of F hat and G hat. And in other books, they write it is equal to 1/2 pi inner product. Both are correct. It depends what definition you adopt. So be careful with the definition is used. I like the definition that is used in Paulsen or Elias Stein, which is mentioned here. It makes many formulas, neater and very clean. So that's our definition. What we can say about f hat. This is again an easy exercise to show that f hat is a continuous and even more uniformly continuous function, is uniformly continuous on R. That's very easy. You just calculate f hat of x minus f hat of y, and you put it inside and use this fact and the dominated convergence theorem to obtain the final result. This is really easy. What needs a little bit of more work is to show that, and this is called the Riemann-Lobeck lemma. I don't need it in this, still I mentioned this. So it's Riemann-Lobeck lemma. It says that lim x tan goes to plus or minus infinity in both directions of f hat of x is equal to 0. That needs a bit of work. It's not that difficult to prove it, but you need some results from measure theory. For example, knowing that function of compact support are dense in L1. So you approximate f by something of compact support, and then you continue. I don't need it in our studies today, but still I mentioned. Another interesting formula, which I will need indeed, it is called the multiplication formula. It says that for every f and g in L1 of R, integral from minus infinity plus infinity f of x g hat of x dx is equal to f hat x gx dx. Even in one book, which I saw indeed 2-3 days ago, whose book was that? Instead of the multiplication formula, they used the, kind of nicer name. They call it change of roof formula. So you can look at hat as a roof, and the roof is changed. It goes from F to G or from G to F. So we can call it change of roof formula too. And it is, again, an easy exercise, this one. First, note that there is no problem with both integrals, because here f is in L1, g hat is a bounded function, even though I did not mention here, but it is clear from the formula that f hat is a uniformly bounded function. And the same here. So both integrals are well defined. And if you plug the definition of G hat here and change the order of integration, which is justified by Fubini-Tonelli theorem, then you obtain the other one. Let me explain. This is not difficult to show. So a sketch of proof, integral from minus infinity plus infinity fx g hat of x dx is equal to integral from minus infinity plus infinity fx. And for g hat, I write it this way, integral from minus infinity plus infinity g of t e to the minus I 2 pi xt dt. And then dx. And now I change the order of integration. I will show you why this is true. I mean, this is an important identity, but why we'll see momentarily. I can write it as minus infinity to plus infinity g of t, and then integral of f of x e to the minus I 2 pi xt dx, and then dt. In other words, I was able to change the order of the integration. And what remains is, I mean, this is integral from minus infinity to infinity g of t. And the other one is simply f hat of t dt. This is what I wanted to arrive at. And the reason I can do this, I can do this change of ordering, is that if you put absolute value everywhere, what do you obtain? Integral from minus infinity. I mean, it's not. Integral from minus infinity to plus infinity. Again, minus infinity to plus infinity, absolute value. F of x g of t e to the minus I 2 pi xt. That's our function, which is a function of x and t, dx dt. Everything is positive. Tonelli theorem tells us that this is equal to integral of fx dx gt dt with absolute value finite. And so if this is finite, then Fubini tells us that we can change the order of integration. Indeed, both of them are needed here. So it's a very simple identity to prove, but on one hand, it's a nice one. On the other hand, it's very useful. We will see some applications of this in our discussion today. So up to now, it's for L1. Is there a formula for f in terms of f hat? The formula we have here gives f hat in terms of f. Probably you have seen a formula like this before, integral from minus infinity to plus infinity f hat of t e to the I 2 pi xt dt, the construction formula, which is equal to f of x. Some comments here. First, the integral should be well defined. And if you take the absolute value here, absolute value of the exponential part is equal to 1. What remains is absolute value of f hat. We saw that f hat is in L infinity. It's bounded, but not necessarily integrable. So one thing we need to add here is that f hat is in L1. That's an assumption to add here. And secondly, when we do this integral, as in the case of the Fourier transform, the function that we obtain here is a continuous function. But f that we started with is not necessarily continuous. So the right interpretation of this identity is that it holds, but almost everywhere on R. In other words, the the function that we started with at the very beginning, if f hat is in L1, the function is not far from being continuous or even uniformly continuous. We can modify it on the set of measures 0 and obtain something which is very nice. So that's the inversion formula, but don't forget that we have an assumption, extra assumption on it. Otherwise, it has absolutely no meaning. So this is the beginning for the theory of Fourier analysis or Fourier transform on L1 of R. In the course I mentioned that we give at the graduate level, we start with Fourier series, indeed with L1 of T on the either interpret T as the unit circle on the complex plane or equivalent to that, the interval 0 to pi, finite interval. So that when we develop the Fourier series or Fourier analysis on L1, one good thing is that for other LP spaces, for P bigger than 1, less than or equal to infinity, LP of T is inside L1 of T. So when we develop a theory for L1, a priori it works for LP too. We don't need to develop a separate theory, for example, for L2. It's already done. But this is not the case for L1 of R. These are not nested spaces. You can imagine, for example, the relation between L1 and L2 like this. This is L1 of R. This is L2 of R. Of course, they have some intersection, but there are functions which are in L1, not in L2, and vice versa, functions in L2 which are not in L1. So, but we have developed the theory here. We have developed the Fourier analysis on L1, so it works on the intersection too. What can we say about the functions which are not in the intersection? And that is the very profound observation of Plancherel, which I mean the starting point of his theory, but that's the most important observation, and everything else comes after this one. Here is his observation. Consider a function which is here, f. So Plancherel observation. Or if you wish, Plancherel fundamental observation, really fundamental. For each f in the intersection, f hat is also in L2 of R. And moreover, the norm of f in L2 is equal to the norm of f hat in L2. Recall that when we are in L1, f hat is in L infinity. But here it maps this part into itself. I mean, it maps L2 into L2. And that's the most important part of his observation, and the rest comes pretty much automatically. The rest is work like this. For any function f, I mean, not necessarily in the intersection, for example, for a function f here, we know from measure theory. So fact, measure theory. In a sense, this intersection, we can say that it is big. What do I mean by saying that this intersection is big? L1 intersection L1 of R intersection L2 of R is dense in L2 with respect to L2 norm, and also in L1 with respect to L1 norm. But what I need is just the first one, is dense in L2 of R. Of course, when I said in L2 of R, it's not needed, but to emphasize with respect to norm 2. So knowing this, we start with an arbitrary function f here. So let f be in L2 of R. Then by the above observation, there is a sequence Fn. Fn is in L1 intersection L2, one property, and the second property, Fn converges to F in L2 norm. True? And so Fn, now we come back here. Knowing this, we see that Fn hat, since Fn converges to F in L2, we conclude that Fn is L2 Cauchy. Therefore, let me call this, I already used a star, let me use this DAG. By DAG, Fn hat is also L2 Cauchy. And we know L2 is complete, therefore there is a function, therefore L2 is complete. So there is a function g in L2 such that Fn hat converges to g in L2. And now we define, F hat to be g. That's the way we define the Fourier transform on L2. Of course, there are some steps to be taken. One very immediate question which comes to our mind is that why this limit g doesn't depend on the sequence we choose. Yes, it is true that there is a sequence which converges to F, but this sequence is not unique. There are other sequences in L2 intersection L1 which converge to F, and when we take the hat, do we get the same function g? This is the case, and I leave it again as an exercise. I said I do not want to cover the course on harmonic analysis, just give you a general picture of it. Yes, it goes to the same function, so I add here g does not depend on the choice of Fn. As long as Fn is in L1 intersection L2 and converges to F, we obtain the same limit. Otherwise, the theory doesn't work. Otherwise, this definition I gave here is meaningless, because with different sequences, you obtain different limits, so F hat is not well defined. And also, if you write this identity for Fn instead of F, norm of Fn also, moreover, for each n, norm of Fn is norm 2 is equal to norm of Fn hat 2. And now let n goes to infinity. We know that Fn goes to F, so this one goes to the normal F in L2 equal to, and this one goes to the norm of G, which we called it F hat. So in other words, the Fourier transform is an isometry on L2. On L2 of R. Well, you can look at up to here, you can look at the Fourier transform like this. I mean, this is our L2 from L2. We know that it maps L2 into L2 in one-to-one and isometric manner. But is it possible that we miss some part of L2? For example, it maps it into here, but there is a part which are not mapped into it. And again, this is excluded. And the reason is that if you look at the formulas we had before for F and F, here, this one, for the inverse transform and the one for transform, they work in L2 with the right interpretation. I will explain what the right interpretation means. And if you repeat these twice, because now when you have F in L2, you can take the transform F hat, it stays in L2. So you can go ahead and do transform another time. The second time you apply the Fourier transform, still it stays in L2. And you can go, as many times as you wish. Note that in L1, we cannot do that, because when we are in L1, F in L1, F hat is in L infinity. We cannot continue. But here, we can continue. It seems at the very beginning, we have a chain, but the chain very rapidly turns into a loop. And the reason is that based on the inversion formula that I just showed you, it was here. It was here. You immediately see that if you apply twice the Fourier transform, F hat of X is equal to F of minus X. And putting hats over hat is not that interesting. Sometimes instead of hat, they use F like this for the Fourier transform. So if you apply twice Fourier transform of F at point X, you obtain F of minus X. So you apply it two more times, you see that F4 is equal to the identity. In other words, the Fourier transform is invertible and its inverse is F3, 3 times. And so something like this is no, English, no, not French. No. Our Fourier transform is more than being an isometry. It's a surjective isometry. So F is onto. Being isometric and also onto, in short conclusion, F is a unitary operator on L2 of R. This is the most beautiful possibility that we can have, and this is not true on L1. On L2, we have a very nice structure. We have something which is one-to-one, onto, and moreover isometric. To finish this part, let me explain what I mean by this. In many books indeed, they write if F is in L2, then F hat of X is defined by the formula that we saw before. f of t e to the minus I 2 pi x t dt. This is for a specialist. You have to understand what this means. If you look at this with I from measure theory, it doesn't make sense because f is in L2. If you put absolute value here, you obtain absolute value of f, absolute value of the exponential is 1, and possibly, this is plus infinity. So if it is easy to provide function in L2 for which the integral explode is not in L1. And so what is the meaning of this? We go back to the definition of L2. We said that you choose a sequence in the intersection of L1 and L2, which goes to F. One of the possibility, not the only possibility, one of them is to chop, is to consider a function fm, which is equal to f, say x is less than or equal to m, and 0 bigger than. That's a chopping in the domain. So in other words, our function could be like this. We consider m here and minus m there. We keep this part. And then the rest, we put it equal to 0. That's chopping on the domain. Sometimes we also need to have functions which are bounded. So if that is needed too, we can chop on the y-axis too. We consider a big n here. Here is minus n, and here is our n. If the function goes above this, we chop here too, and put it equal to n here, and the same for minus n. But for the time being, suppose that I chop just on the x-axis, so I don't enter into this now. And this function fm is in L1 intersection L2, and fm goes to f in L2 more. Then m goes to infinity. Therefore, based on the Plancherel theory, so Plancherel theory, fm hat goes to f hat in L2. But what is fm hat? Fm hat, we know precise formula for it because it is in L1. Fm hat of x is equal to integral from minus infinity, the original definition, fm of t e to the minus I 2 pi x t dt. And then because of the way we chopped, it's integral from minus n to m, f of t e minus I 2 pi x t dt. That's fm hat. And this goes to f hat. That a better way is to write like this: f hat of x is lim, which means limit in the mean or limit in L2 of f hat, fm hat of x, or lim in mean integral minus n to n f of t e to the minus I 2 pi x t dt. That's the correct way, or more precise way of writing this. That's at the beginning, but mostly, the specialists forget about this precise way of writing lim in mean, and they simply write f hat of x equal to integral from minus infinity to infinity. So you should keep in mind what this means. This means a limit is hidden here in this formula. And the same for its inversion. I mean, f of x equal to integral minus infinity plus infinity f hat of t e to the I 2 pi xt dt. It has precisely the same meaning as before. This is a limit in L2, limit in min. If you keep this in mind, everything goes well. Another consequence of indeed, I mean, I should go at the very beginning, so I stay here. You remember the multiplication formula or the change of roof formula, which was for L1. So I repeat the formula here. Multiplication. It was integral from minus infinity plus infinity f of x g hat of x dx equal to integral from minus infinity to plus infinity, change of the roof, dx. For every f and g in L1. So in particular, you can pick if you start with f and g in L2 of R, you can pick Fn is in L1 intersection L2, Fn goes to F in L2, and the same for G, Gn in L1 intersection G2, Gn goes to G in L2. And this formula is working for Fn and Gn. And then let n go to infinity. When n goes to infinity, we know that when Fn goes to F, as a consequence of this, Fn hat also goes to F hat in L2. The same for Gn hat. So from this, by taking a limit, we immediately, the same formula works. But this time, change of the hat, change of the roof formula. This time for all F and G in L2. And again, there is no problem with the integrals because on the left side, for example, F and G hat both are in L2 by Cauchy-Schwarz. F times G hat is in L1. The same for the right side. So absolutely no problem. What is the consequence of this, which I need after the break, is instead of G here, this works for all F and G in L2. Instead of G, write G hat. So it becomes F G hat hat twice. And here it will be F hat G hat. And we saw that G hat hat twice is G of minus X. So it will become integral F of X, G of minus X dx is equal to integral from minus infinity plus infinity F hat of X, G hat of X dx. Again, this is by itself an interesting identity which works in L2. We cannot do this in L1. What I did, I simply replaced G here by G hat and obtained this. And if you want to go one step further, if you don't like G minus X on the left side, still it is possible to replace it by G of X or call it a function, a nice formula. Define h of X to be G of minus X bar. This is better. And you see that this formula immediately transforms to integral from minus infinity f of x h of x bar dx equal to integral minus infinity plus infinity f hat of x h hat of x bar dx. It's more symmetric this way if you define this change of function. And that's the Parseval, one version of Parseval identity. Usually we write it as f h inner product in L2 is the same as f hat h hat inner product in L2. And if f is equal to g, we saw it before. Indeed, that's one way to arrive into this Parseval identity. Another one is to start from this and use the polarization identity to give the previous one. These two are equivalent. So it depends which way you want to adopt. But at the end of the day, we have something symmetric and very interesting, and it plays an important role in our application after the break. Any question up to now? Well, if not, let's see what is in the chat. Okay, there is a book by Sheldon, very interesting one, and the link is provided in the chat. I think it's for free too, that you can download. It was one of the Springer offers to the students and researchers. So is it true, Sheldon, that the book is for free now?
Yes, the electronic version is in, it's an open access book. So the electronic version is legally free.
Okay.
So feel free to download it.
Sure. And all discussed here, the L1 theory and L2 theory is there. Everything is there, and you can go and see the details of it. Thanks again, Sheldon. So we have a break now, a break of about 10 minutes, and we come back.